Okay, let's talk about your homework. Let's talk about it.
That's donut about. Do not think about. 9 as well.
9 and 15. We're on page 420, yes?
Yes, ma'am.
Ooh, 9 is about the y-axis.
Yeah. But it was also like the tangent.
Okay.
Yeah, I don't understand how to read this. What is it?
Well, I was going to say, this is a calculator problem. My first clue that this is with respect to y is that the equation is given to me in x. The second thing is it forms a solid at the y-axis, right? So it says that generated about the y-axis here as it rotates around. So remember, I still only need the radius, right? And the radius is from here to here. So what is the length then of the radius? Tangent. That's right. Do we all agree? So now I do, right. So the area of one circle is going to be pi times r squared. So the volume of this thing rotating around is going to be the integral from 0 to 1. Why am I doing from 0 to 1? I'm looking on the y-axis. That's exactly right. And if you're using your calculator and you want to throw an x in here, you could. The variable itself doesn't matter at this point. Pi and squared pi over 4. If you put a y there to put on your calculator, that is a-okay. But this goes straight in your calculator. We'll just put the x. Just put x. Because the variable itself doesn't matter at this point, right? Because you're still going to find the derivative the same way. Does that make sense? So, I don't have my calculator. All right. So what?
When I do it,
You're talking about because of all these pi over 4s and all? All right, so whenever I put this in, I would do tangent squared and I'm actually going to do it like this because your calculator won't let you square right there. And then we've got pi over 4x. That closes out the tangent function, then close the whole tangent to square it, right? 1, 2, 3, 1, 2, 3. That make sense? Now I can calculate. I can go math. I'm going to do y1 x from 0 to 1. And then I have to multiply it by pi.
so on your graph, if you put the integral function on there to find the area, because I've done that.
The answer was 4 minus pi. They didn't use the calculator. I was just making sure. Say that again.
When you are graphing and you want to like combine stuff, can you put the integral function into your graphing part of the calculator? find the area under the curve.
What do you mean?
So can you go to white, math 9, when math 9 again, so math 8.
Oh, if you want to do that, just when you're in, when you graph it, I'm going to do a zoom trig on this. If you're wanting to find the integral in here, if you go second, trace, calculate, and then do number 7 there, then tell it the limit from 0 to 1.
So what are you trying to find right here?
It does work. If you're talking about area, it does if you multiply that by, then multiply that by pi. It's pi
So
r.
what is not included there? So you include pi in our point. So could you put the pi back in and like our equation?
Yes, you could. So if this was that, the reason it works is if you rotated that graph around and it was on, regardless or not, if you've got discs that are being cut out this way or this way, if it was on the x-axis, since there's only that one variable there, it works. There's no hole or anything there, so it'll work brilliant. So now if I did the integral from 0 to 1, I should be back at that 0.8 something. He said, could you put the pi inside of it instead of multiplying it last? And you can, because, so yeah, that's just the other way to do the integral. Second trace down to the integral, and then all you have to do is give the bounds, 0 to 1. It's a little easier than doing it this way, function manager. Thank you.
So y1 max.
Yes. Yes, but you would have to get each value and then subtract.
So
Wait, so how does it look? You have to input those graphs like separately?
Yes. You would. Does that make sense, everybody? Do we know the antiderivative of theta squared? I don't feel like we do.
why can't we look it up? What is
No. We're going to use the calculator because it's a calculator problem. Number 19. Oh, 15 and 19. Were they? Oh, I'm so sorry. It's been a long time ago, Katie. Friday feels like a lifetime ago. Awful. 17's a washer. You'll know how to do it after today. Bless you. X equals 0. So it looks like this is the piece that I am rotating. Agreed? And you'll see today that we could do this with a washer about the x-axis, but it asked us to, oh, it does say the volume of the sun. This is a washer problem. Unless you did it about the y-axis. Now the y, you could do it about the y-axis, but it specifically said generated about the x-axis, revolving the region bounded by lines and curves about the x-axis. So to do it about the x-axis, I'm going to have a hole. You do it about the y-axis. I'm going to say my radius on this one. I'm going to do it about y, just so I can show you. Do it about y here, the radius, and it's going to rotate about y, even though it said to rotate about x. So here, the radius would be what? But I'm going to do it, remember, in terms of, I'm going to say it's y, because I'm going about the y-axis, just to show you what's happening. This is y equals, what did I say, 1? So the radius is y, so the area is y squared, so the volume would be pi times the integral from 0 to 1 of they probably did a washer, but we should come back to the same thing. Let's see. Well, no, we shouldn't come back to the same thing they did. We rotate that way. What's that look like? That looks like a cone. The other would have a hole in it. Let's see what we get here. This would be 1/3 y cubed from 0 to 1. Bless you. Well, what they did was, if you looked at the directions, it was over the x-axis, and we haven't talked about that yet. If you rotate this piece and you make this your radius, right? There's a hole in the middle. Do you see that? If I'm rotating it about this, so almost like the donut we were talking about, it'll have a solid bottom right here where it meets, but it's gonna have it's gonna be like a shell that gets thicker as you get to the bottom. Envision it? I know. All right, what else on your homework? 41. Finally, here's one that's not a washer. It's a cross section. The base of a solid between the regions y equals 2 root sine x and the interval 0 to pi on the x-axis. The cross sections perpendicular to the x-axis are, the first one they say are equilateral triangles. So I have this, there's 2 times the square root of x, something like that. They even drew the picture for you, nice and neat. That's the base of my triangle that's coming up out of here, however it goes. So, what's the base of the triangle? That doesn't give me enough to get the area though. That's the base. Remember, area of a triangle is 1/2 base times height. That's the base. I need the height. I'm going to drop down 90 degrees. That's the curve. That's this curve right here. Well, for one, there was a picture that went along with it, and it showed me. But it said that the equilateral triangles with bases running from the x-axis to the curve. So from the x-axis up to the curve is the base. And so what is that distance? Well, if this is 2 root sine x, that's the distance. All right, so I need that drop down height in the middle. I have a 30, 60, 90 triangle, and I have the short leg, right? Now this whole length is 2 root sine x, but what that means is, right. So it goes x times the square root of 3, 2x. So what is the,
So which one is
That's the whole base here.
That's also good. Would just be square root of 3 sine x, right?
Yes. So this side, which is this, would be the square root of sine x times the square root of 3. So I can put this together as the square root of 3 sine x. Correct. So now the area of just one triangle would be 1/2 base 2 root sine x times height that's right. Square roots cancel, except that square root of 3 is still under there. So it's going to be square root of 3 times sine x. So now, no, because they were under a radical to start with. So you could write it, you could do this, 3 sine squared x. But that's still not what I was asked for, because I was asked for the volume of the solid. So the volume from what to what? 0 to pi. Could definitely do this one without a calculator. What is the antiderivative of sine x? Negative cosine, right? Because the derivative of cosine is negative sine. So negative cosine x. This was not a circle, this was an equilateral triangle. So remember, these cross sections are where I have to think about different. That would have come up here if I was doing that. Once you find the area, it goes into the interval, area of whatever shape it is. I know. Okay. All right, plug them in. Root 3, I've got negative cosine pi minus negative cosine 0. What is the cosine of pi? It was said with such confidence. The cosine of pi, -1, but the negative's already there, so it becomes 1. Minus, what's the cosine of 0? 1 minus -1 here. So this would be 2 root 3. That's the answer. Do you need me to do the other half of that for the squares? Part B said squares with bases running from the x-axis to the curve. That was actually easier. If this was a square and this was the base of the square, then the area would be right. 2 root sine x squared, which would be 4 sine x. So the volume would go from 0 to pi, 4 sine x dx. Yes. Y'all do not like these cross sections, do you? Yeah. 8, yes, that's the answer, 8. 44, the base of the solid is the disk, x squared plus y squared is less than or equal to 1. X squared plus y squared equals 1 is actually a circle of radius 1, right? We all know that. The cross sections by planes perpendicular to the y-axis between -1 and 1 are isosceles right triangle with one leg in the disk. So that's right. This is x squared plus y squared equals 1. I've got an isosceles right triangle. Does this, and it says that is the one leg in the disk. It doesn't say, oh, it's isosceles right, so So that means this distance is one of those two legs, but those are the same thing. So now the question is, what is this length? And this is one of those things where we have to think about it, solve it in terms of y, and double it for that length, right? Y'all remember doing this? You know what I'm talking about? So this would be y squared equals 1 minus x squared. So y is plus or minus the square root of 1 minus x squared. This would be the positive up top. This would be the negative on the bottom. So what is one leg of that isosceles right triangle? This is an isosceles right, what? It should be. It's, okay. Maybe it did whenever I clicked it. So now what is the length of the leg there? Or no, what's the length? I'm sorry. The hypotenuse. It's a, that's right. How'd you get that? Go ahead, Lizzie. It's a 45, 45, 90, which means whatever these are, you take that length and you multiply by the square root of 2. Oh, we didn't even need that. It doesn't matter. Because what's the area of one triangle? 1/2 base. I'm sorry. So it's 1/2 1 minus x squared. And now I integrate to find the volume. From what to what? Negative 1 to 1. 1/2. 1 minus x squared. It's a circle of radius 1, so it goes out. Negative 1. Y'all want me to finish integrating that? X minus 1/3 x cubed from negative 1 to 1. One minus 1/3 minus negative 1 minus negative 1/3. 1 minus 1/3 would leave me with 2/3 and negative 2/3. One half times 4/3, which would be 2/3. Right? Did I do that right? Anything else? Anything else? Take a brain break and we'll do. This is if the triangle sat here, but we needed to double that. You're right. Right. Thank you. So there would be a 2 here and a 2 here, which would be 2 here, which would mean this is 2. Still doesn't give me 8/3. Oh, yes, it does. Huh? Circle won't be due till Friday when we have the test. It'll be in addition to stuff. This is the hardest track. Yeah, I know, and we've only done 3 lessons out of it. We have been in section 3. This is like the 3rd or 4th day we have been in section 3. Don't say that already, Dylan. What? I feel like this is hard, but it's.
I mean, I would pass the AP exam, but.
Wait, so we did article mention, then area. Like, what's the whole, like?
This is still volume of revolution. Oh, yeah, applications of integrals. Is that what you're asking?
No, I was asking about
This is still volumes of revolution. The 7.3 is volumes. And we talked about volumes of solids that are cross-section. And we talked about volumes of revolution. And now we're talking about we're talking about volumes of revolution whenever there's a hole. So in other words, but it really does make sense if you think about it. I don't know. I think because it's like a college level. All right, cosine and sine, ready? I want to know the region in the first quadrant enclosed by the y-axis and the graphs of y equals sine and cosine when it's revolved about the x-axis to form a solid. So graph it, graph it, graph it. That's going to be the only way to do this. So let's graph it quickly. I know it's bounded by the y-axis because it tells me. Bounded enclosed by the, so I'm just in this first quadrant over here. I'm going to take this up to 1. Here's my pi over 2, my pi. And these are easy parent graphs, right? The cosine of 0 is 1. And then it comes down. I'm not going to have to worry about any of this because as it comes down and back around, I'm already past the x-axis. But I will go ahead and do and then I'll kind of zoom in on it some. Sine x, the sine of 0 is 0, and then I jump up to, so this one does something like that. So the point that I'm getting to is I'm looking at this area right. Everybody good on what we're looking at? Now, the problem with this lies if I have to rotate it about the x-axis, what did you notice? There's a hole. Well, because if I took this whole green piece and I just flipped it around the x-axis, right? All this is this black hole. There's nothing there. There's no as it rotates around. There's no graph there. You see that? You're exactly right on what you're thinking. So if this is my axis, I'm taking this piece and I'm wrapping it around until it meets back around. Let me see if I can find a visual for you.
Like this one, it's like pieced apart. You know what I'm saying?
I feel what you're saying.
I'm hesitant to show anything that I've not watched before. So this first one is the disc, right? It's solid. As you rotate it around, it makes this solid. I'm taking out solid circular pieces. But this one, there's a hole in the middle of it. So as I rotate around, I'm still taking out disc, but my discs are missing a hole in the middle. each disc has a hole. That's why we say washer, because we're taking out a circle. The whole thing is not a washer, but the piece you take out is a circle with a circle in the middle missing. Okay, at that point, no. At that point, it's not. That's the only point it's not, though. On the what?
So it's just like it's like continuously becoming smaller.
This is the hole. Right, right. So whenever I take out my disc, right, I'm looking for a disc that's this shape, is essentially what I'm doing, right? But because I'm on this, because I'm on the x-axis and I'm rotating around the x-axis, this part right here is a hole, and it gets bigger as I go that way to the right, but it's still a hole in it, right? Is what connected?
Like if we're rotating around the x-axis, right?
Mm-hmm.
So then it would make the shape. What's the bottom?
Yes, the bottom bit. And let me show you this picture that's in your book, because this might help you. I shouldn't have done mine. Because I think and you really don't, it's good to visualize emotion. At the same time, you can just learn the method of doing it right. You're still doing the same thing. All right, this is my little piece that I'm rotating, right? And it's rotating about. This is the shape that it forms. You see the hole in the middle? That's the hole, that's this area right here, all the way down. But I'm still taking a circle out each time that has a hole in the middle. So that's why we call it a washer. It looks like a washer as I pull these discs out, because they've got a hole in the middle. Does that make sense? So essentially what I'm going to have to do is find the area of the pink one and subtract the area of the hole, right? Okay, is everybody okay with that? So, well, we're going to integrate, we're going to kind of put it all together. We're going to say, let me show you. Because subtraction, I can, doing this blah minus blah, I can put them together as blah 1 minus blah 2 in the same, right? Okay, so that's kind of the thought process that I'm going. The only thing I'm going to have to do here is definitely find this intersection point, right? Let's do that first because that's easy. That's easy peasy. Where does sine x equal cosine x? Pi over 4. We know that from the unit circle, right? Pi over 4, they're both square root of 2 over 2. We just need the x part because we're integrating with respect to x, so I'm just going to say x pi over 4. Of course, it starts at 0. So now let's think about it. Let's do the area from the top first. So this is what we call, you'll see this referred to as big R sometimes, big radius, whole radius, right? So the area of the whole disk without the hole. If there was no hole and that was a solid all the way down there, what would be the area of that circle? So the area with big R. That top one is what? Cosine. So it'd be pi R. What's big R? Okay. So we all agree that's the area of the big one, right? Now I need the area of the hole. So little r. So that's pi sine squared x. Well, watch what happens. This one actually comes out to be an identity when you do it. Cosine squared minus sine squared is cosine 2x. Now one, sine squared plus cosine squared is, it's cosine 2x. That's one of those identities. We're going to practice with those as we review. I have a packet of stuff of things you need to know cold. All right, so if I were just doing, Dylan, this curve, right? The radius then, the radius of the whole thing would be cosine x, right? So I do pi r squared. If you were doing it as a solid like you did before. Now I need to know the radius of the whole. There. That is the bottom curve, which is sine. So what I'm doing is I'm finding the area of the whole, and I'm subtracting, wait for it, the area of the whole. Ah! But yeah, exactly. That's what, yes, it is. It is. This is washer. You got to subtract out the whole. You've got to do it twice. Visualizing it, it's still top minus bottom. That's exactly what it still is. But you got to do the area, right? But it's top minus bottom. Twice what? No, I was just saying whenever you subtract here. So this is gonna, well, this is gonna be the integral, right? From 0 to pi over 4. I'm still gonna take this pi out because they both have a pi. I'm gonna put it on the outside, and I'm not gonna worry about it right now. No, I did not. Cosine 2x. Mm-hmm. This is an identity. I believe. Okay. So there are cosine, the double angle identities are pretty popular for things to know. I'm trying to think if there was a way you could get there from 1 minus sine squared, 2 sine squared, 1 minus 2 sine squared. It's still. Okay. Sine squared plus cosine squared is 1. But cosine squared minus sine squared is cosine 2x. Okay, so now this becomes an easy problem, right? Finish this out and see what you get. Don't forget your chain rule here because this is or use substitution however you want to do it, but you need your du to be 2dx. It's not. It's not.
Do you do the chain rule in when you chain rule, do you take the antiderivative of 2x? Or do you just take
No. Well, when I say chain rule is really only for deriving. U substitution picks up the chain rule for integration. So if you let u be 2x here, then du would be what? 2dx. Right? So I need a 2 here, which means I need a 1/2 out here.
I did x squared. I got the antiderivative.
Couldn't you do x du? No.
Does this work? Can you just do x squared?
No, well, that is du. So now I'm pi over 2 from 0 to pi. Have y'all forgotten how to do substitution?
Yeah.
If you know the antiderivative of cosine 2x, is it? You're saying the derivative of 2 sine x is cosine 2x? You did, right. But remember, this is changing my bounds if I do this. So this is going to change this because u is 2x to pi over 2. What? How can you just make, no, you can't do that. Because if I do use substitution of a definite integral, I have to write my bounds in terms of.
Okay, but when do you plug, okay, right.
Also,
I
there
think I
was
screwed up on
one,
the test.
there was one where there was a substitution on like it was a home, and they didn't switch the bounds, so I was confused.
Okay, so if you don't have to switch the bounds, but what you have to do, if I left the bounds what they were, remember I told you there's two ways to do it. You'd have to, like, the antiderivative of cosine is sine, right? So sine u, and I've got this pi over 2 on the outside, right? I can't just plug in pi over 4 and 0 because that's in terms of x. So what I'd have to do is pi over 2 sine of 2x. This is evaluated from 0 to pi over 4.
You plug in it's from 0 to pi over 2.
Or this is two different ways. Cosine u from 0 to pi over 2. Both of those will give you the same thing. But you have to take your u sub into account when you're bounded like that, when you're a definite integral. And that's that, so you did that way, and that's fine. Don't do it twice. Don't sub u back in and write your bounds in terms of u, because then you're gonna, yeah. Why not what?
After you change it in terms of you, and then you sub you in.
If you sub u back in, don't change your bounds. Okay, so these bounds now, the way they're written are in terms of x. If you have a u in your answer, then you need your bounds in terms of u. If you haven't, see, this is in u, so I need my bounds in terms of u. This is x. It was originally in terms of x, so I keep it in terms of x. Okay, so if my u is 2x, then my du is 2dx, so I need a 1/2 out here to counter that. That's right, Lizzie. What? I didn't take the, I got all into mine.
No, but you can't do that.
Why?
It said don't plug in your u. Oh, wait. I thought it was sine u, not sine pi over 2. Or x.
Yeah.
Okay,
Sine of pi over 2 is 1. 1 minus the sine of 0 is 0, so it's pi over 2. If I did it this way, yes.
This is why I missed all these freaking questions. Me too. You don't know when to plug. I plugged it into the. You get new bounds and
Yes.
you don't when you like you do sine u minus sine u of the bounds. You don't plug pi over 2 in. You don't plug pi over 2 into the u.
You plug pi over 2 in for u, but if you change it to x, you use pi over 4. It depends on, they have to be in terms of the same variable. This is saying, right now, the way it's written originally, this is saying when x equals pi over 4 and when x equals 0. But if this is u, you can't put what x equals because x isn't in there, it's u. Well, what does u equal when x is pi over 4? Well, u equals, yeah, you do. I already did it though. Originally it was pi over 4. I changed it to pi over 2 because I plugged in this. You always go back to what you let U equal and plug in for your bounds.
I did too much.
Well, I don't
No,
know about that.
I got new balance and also plugged in for you. That should come up, right? I got new balance, I plugged into you, and then I also plugged my FLP myself.
Yeah, no. Right.
That's why my equation was so long. What? So I gave you that like really long.
There are four different revolutions I have to do with this problem. I know. Find the volume of the solid generated by revolving the region bounded by these things about, and I'm going to do the x-axis, the y-axis, and then I'm going to do two different lines. So let me just graph it first and show you what we're working with here. I know. Oh my gosh, shut up. There's y equals 2. X equals 0 is obviously my, yes, 31. And then the square root of x, which 0, 0, 1, 1, and then terrible. All right, so here is my piece. Yes? I'm just going to set these up and not actually work them through for you so you see. There'll be different shapes depending on how you revolve them. It depends on where your hole is. So about the y-axis is a solid, and that's an easy. Okay, so let's do x-axis because x-axis has a hole, so we're going to have to do hole minus hole. Yes, it tells you. So part A says revolve the piece about the x-axis. Okay. So my hole is from here to here. My W hole, my whole hole. It gives you these two equations and it says rotated about the x-axis. Because if I'm rotating about the x-axis, then the whole thing goes down to the x-axis. The H hole is the part with no shading to the x-axis. So my whole hole, my W hole, right? My entire hole, the radius is just y equals 2, right? So it's just 2. So the area of the hole is pi times r squared, so it's 4 pi. Because this line is y equals 2. The area of the hole, or the radius of the hole, square root of x. So the area, so that's just the radius. So the area of the hole is pi times the square root of x squared, so it's just pi x. So to find the volume, I go from 0 to 4, because that's where they intersect. I'm going to throw that pi outside, because I'm not even going to, everybody's got a pi, so put the pi outside. Leave it alone. Huh? Now, I'm going to let you finish that one because I want to show you this rotated about a line.
pi, 1 minus 6.
The answer is 32 pi over, nope, 8 pi. You serious right now? Hurry up. Okay. If I did it about the y-axis, this time my radius, I don't have a hole, I just have a solid, right? There's no hole. But this needs to be in terms of y instead of x if I'm going about the y-axis. So about the y-axis, I don't need a hole minus hole, I just need a hole, right? A hole, like a W hole, okay? So I need, this would be the same as x equals y squared. This time I'm going from, all right, so let's do the area first. The area, well, let's do radius because that's what we're doing. The radius would be y squared. Yep, we got to do it 4 ways. Pi r squared. That's my area of this circle that I'm pulling out. So for the volume, from 0 to 2, again, I'm going to throw that pi outside, y to the 4th dy. 2, 4, 8, 16, 13. Because it's in terms of y. Now, what I really wanted to get to, and this is where you have to think about it. What if I asked you to revolve it, not around the x-axis or the y-axis, but about the line y equals 2? So instead of going down with the shape, I'm coming up with the shape, right? So this is rotating upwards. I don't have a hole anymore, right? If this is the line, it's a solid. You don't have anything to subtract. Exactly. So what is your radius there? Well, if you're rotating parallel to the x-axis, then you're in terms of x.
I like that.
So what's your radius?
Y squared.
No, it just said
2 minus 3. Well, because you got to get it.
Okay. What is that length? Yes, the red part. 2 minus square root x. I'm sorry, no, I went. 2 minus square root of x. Once you've identified the radius, it's downhill from there because, then you just do the area, right? Because I need this pink part, but the distance of that, I have to take in, here's square root of x. Square root of x is this little blue part. The whole thing would be start at the top, that's 2, but take away the square root of x to find what's left there. I'll post your homework.
What's the difference in that and what we already did? Is your balance changing?
Just what you're rotating about.
No, I know that, but when